My name is Johnson from the International Hurricane Research Center at Florida International University. I'm going to talk about our study on mangrove attenuation effects on storm surge using the TELEMAC2D hydrodynamic model. The objective of this study is to improve the understanding of mangrove attenuation rate through detailed pneumatic modeling. And we particularly consider a mangrove area surrounding a river system in order to see how much the river effects are on mangrove attenuation rate. The pneumatic modeling is through the CEST storm surge model and the TELEMAC2D inland flooding model. The CEST model is more regional and is used to provide the coastal boundary conditions for the local refined TELEMAC2D inland model. This slide shows our study area, which is a mangrove zone at the west coast of South Florida, USA. And we selected the 2005 Hurricane Wilma as case study. This orange line shows Wilma's track around the landfall. Wilma has caused about 4 to 5 meters high storm surge around the mouths of Honey River and Shark River, as you see here, which is our focused simulation area. Gauge measurements by the USGS are available for model validation. This slide shows the generated unstructured grade. Around the Honey River and the Shark River, the grade size is as small as 5 meters to resolve very small creeks. And this slide shows the interpolated topographic and bathymetric data on the left-hand side and the manning coefficient map on the right-hand side. Now I show you some results. This slide shows the validation of the water level time series at the USGS river gauges. The red lines are the computational results and the black dashed lines are the observed data. In general, the model results compare well with the observation in terms of the peak water level and the arriving time of the peak water level. Even at station SH2, which is about 18 kilometers to the coastline, the model still predicts a good result, which verifies the current model setup. In these slides, I'll show you two animations of the storm surge induced by Wilma. We also manually remove the rivers and run simulations to show the river effects. Which is placed on the right-hand side. Now let me play the normal one with rivers first. As a surge propagates inland, it would first follow the river path and cause river levels to rise ahead of the main surge, which may cause river flooding as the main surge keeps pushing inland. While on the right-hand side, when the rivers are manually removed, this phenomenon is not observed. This slide plan presents the maximum storm surge profiles at two locations. One is the red line along the path without much river channels. The other is the black line along the Shark River. The right-hand side figure shows the maximum storm surge profile, and the colors corresponds to the profile color, as you see here. The solid line represents the normal case with rivers, while the dashed lines represent the case with the rivers being manually removed. As you can see, when the rivers are artificially removed, the maximum storm surge profile at both locations tends to decay faster than those with the rivers, which indicates a negative effect of the rivers on the mangrove attenuation rate. And this table here shows that the negative effect of the rivers on storm surge attenuation rate can reach as much as 15% along the Shark River and a relatively small 6% along the red line profile. So to summarize, this study shows that around the Honey River and the Shark River, the mangrove attenuation effect is about 30 centimeters per kilometer on the maximum storm surge height. And the results also show that the rivers do reduce the mangrove attenuation effect on storm surge by up to 15% along the Shark River. And finally, the TELEMAC2D model with refined grid and the nesting techniques proves to be an effective method for such a study. Thank you.